Welcome back to my channel. In this video we are going to find the equation of motion of a simple pendulum by using Lagrangian method. Also we use the same method to deduce an equation for the time period of the simple pendulum. We can pictorially represent simple pendulum like this, as a string is connected to a rigid mass m and it is attached to a support. Let us assume that the angle made by the simple pendulum at any instant be theta, that is the angular displacement of the simple pendulum from the equilibrium position. This is the equilibrium position. Angular displacement of the simple pendulum from the equilibrium position be taken as theta, and assume that L is the length of the string of the simple pendulum. Actually we take it as the effective length, L as the effective length of the pendulum, m mass of the bob, and theta angular displacement. Let us mark this point as C and this as B, and this is the trajectory of the pendulum, and here we can take it as O. This is B, this is C, and this is O. At any instant time, let it be at the position making an angular displacement theta, and we denote this position as A. This is our bob in some position. We can, using the equation, we have the equation angular displacement theta equal to arc by radius. So using this equation, here we can also write theta equal to, we denote this arc as S and the radius by L. So arc here it is S divided by L. So the displacement of the bob S equal to, the arc is equal to L into theta. Now kinetic energy T equal to half mv square. Here the displacement is taken as S, so it is equal to half m into, that implies V equal to L theta dot. So half m into L theta dot square, that is equal to half m L square theta dot square. So kinetic energy is half ml square theta dot square. Now we are going to take an approximation, that is the potential energy of the system when the bob is at O is 0. Potential energy is 0 when the bob is at the position O. We take an approximation, potential energy V equal to 0 when the bob is at the position, when the bob is at position O. So the potential energy when the bob is at A is given by V equal to mg into OB, because it is above the height. The height here is h equal to OB. We know that potential energy is mgh. So here the potential energy is mg into OB. It is equal to mg into OC minus BC. OC minus BC. OC minus BC. OC is this distance, BC is this distance. So OC minus BC will give the distance OB. And it is equal to, what is O? OC. BC is equal to OC is equal to length L. OC equal to length, effective length of the simple pendulum, but we don't know what is BC. From this picture, we can say that BA equal to or AB equal to L sin theta. Also BC equal to L cos theta. So BC equal to L cos theta. OC equal to L and BC equal to L cos theta. So this is equal to mg into L minus L cos theta. That is equal to mgl into 1 minus cos theta. So kinetic energy is half ml square theta dot square and potential energy is mgl into 1 minus cos theta. So we obtained that kinetic energy T equal to half ml square theta dot square and potential energy V equal to mgl into 1 minus cos theta. So now we can form the Lagrangian L equal to T minus V, that is equal to half ml square theta dot square minus mgl into 1 minus cos theta. Now dou L by dou theta equal to minus mgl sin theta. Similarly, dou L by dou theta dot equal to half ml square into 2 theta dot, that is equal to ml square theta dot. We have the Lagrange's equation as d by dt of dou L by dou q dot minus dou L by dou q equal to 0. Here the independent variable or the generalized variable is q equal to theta. So the equation changes to d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. Making substitution, we get d by dt of ml square theta dot minus mgl sin theta equal to 0. That implies ml square theta double dot plus mgl sin theta equal to 0, or m and l are common in both terms, so we obtain theta double dot plus g by l sin theta equal to 0. Theta double dot plus g by l sin theta equal to 0. This is the equation of motion of a simple pendulum. This is the equation of motion of a simple pendulum. So we obtained an expression for the equation of simple pendulum as theta double dot plus g by l sin theta equal to 0. For small amplitude oscillations, that is when theta is small, we can approximate theta as it is approximately equal to theta, sin theta approximately equal to theta for small amplitude oscillations. So the equation of motion now takes the form theta double dot plus g by l theta equal to 0. This represents a simple harmonic motion and it is similar to theta double dot plus omega square theta dot equal to 0. So we can relate these two terms as omega square equal to g by l or omega equal to root g by l. We know that time period is related to omega, angular velocity omega by 2 pi by omega. So here the time period t equal to 2 pi by omega equal to 2 pi root L by G. This is the expression for the time period of a simple simple pendulum of length L. Thank you for watching the video.